Good evening, everyone. So as Hamza said, my name is Jakub. To introduce a bit myself, I'll try to make it a bit smaller. I'm a Python software / data engineer / scientist, now working at Quantlane. We are a trading company. We run our own trading platform. Most of the code base is Python. And as Jan said, my roots are rather long in academia, and I was doing mostly numerical simulation in fusion research. And today it's my pleasure to talk about Python optimization for numerical calculation. So Python is slow. This is what I hear many times. And the question I pose today, is it really? And the answer is it depends. And also the answer is, even if it's slow, we can optimize when appropriate. And I'll try to give you some motivation and some overview of how you can actually do that. Now, you've heard maybe that perimeter optimization is the root of all evil. That's a frequently cited phrase, and it's kind of true. So follow that, because you, of course, you need to assess. You need to know that before you optimize, you need to decide what to optimize for. Typically, you have to trade the total costs, which are the development cost, human work, the computer time, and your gain is your profit. So don't try to optimize too early with an unknown goal. So what are the typical optimization goals is we often think of faster execution, so less CPU time spent in a calculation. We should also think about less memory consumption. That can be, because that can bring resources, like even in terms of money, if we run in the cloud or we need to buy the hardware. And we should also look into how the performance scales with the problem size. So those are, I think, the three main things to optimize for. And also one nice thing to remember always is that there's a Pareto principle, which states that 80% of the effects come from 20% of the causes. Now you can change the numbers a bit, but for code it means that basically 80% of your CPU time is spent in something like 20% of the source code. So your goal is to identify these 20% first and then to optimize those 20%. And don't forget to consult XKCD, of course. So to actually identify the 20%, the tool you would use is a profiler. So here I give you just a short list of tools that can be useful. I'm not going to touch this topic too much, or basically not at all. So just keep it for reference. And instead what I assume that we've already found a good reason to optimize something, and we do that here today. And the target of our optimization today is a numerical calculation. If one were to optimize something different, like a general Python code, the tools would be different. It might overlap, but in general, it could be quite different. So there's a test example, which I actually have stolen from Jake Vanderplas' talk, but it's nothing very special. It's an Euclidean distance calculation of a set of vectors. As I said, we are at the point that we have found that this is the bottleneck of our business. So let's try to optimize that. So I'll start with just some random data as input, which I will use throughout the presentation to demonstrate the performance and the steps that I'm doing. Now I think we probably all or most of us know that Numpy would be the #1 choice to do this kind of calculation in Python. Here you see, I think I can make this bigger again. So you see how this is implemented in Python. And one particular thing that is handy in this case is broadcasting. So Numpy can kind of automatically broadcast or extend the dimensions, and we use it here to do the pairwise calculation and do sum reduction to actually get the results we want. So it's a one-liner. It's really short, and it does the thing well. Now I'm going to use %timeit, which is an IPython magic for just getting some statistics about the runtime. So in the background, it would run the command that I give it multiple times, and it will yield some statistics. And I'm storing that into a dictionary, which I would then use to compare the times. So we are at 40 milliseconds for this case. Actually, these results were just run before the presentation on my laptop, which is not the newest, most performant one. If you run it on your server or even on a modern desktop, you would get probably lower numbers. And also, I'll talk about that later, but you can get very different results in terms of ordering the approaches. So let's ask what kind of performance we get from Python loops. If I teach Python, which I do at the university, I typically emphasize that something like for I in range something is a typical anti-pattern, and we often do either iteration on some kind on the list and get the items themselves, but in numerics we do vectorized operations with Numpy. But here I will demonstrate how performant it is, and later I show that it's actually handy to have this implementation anyway. So here's a loop code that looks like C code. So for those who are used to code in C, C++, you would do that and it would run well. Now if I run it, it takes 5 seconds, which is way much slower than the Numpy performance. So here you see a comparison. Mind that the y-axis is in log scale, so we get something like 2 orders of magnitude difference in the runtime. Okay, so now we would answer to our initial questions that Python is slow. Well, let's see. As you probably know, we should really test that the function we are implementing is doing the right thing. So I'll just put in, after every implementation, I just do a simple assert. Now, we can do that with Numpy all and compare the numbers. It's not the best idea because we have floating point arithmetics. So what's better is to use all close, but with a low tolerance. So we are pretty confident that we are happy with the result. So that's my assert we are happy function here. Okay. So number 3, possibility for optimizing the code that the function that I presented is Cython. So Cython is quite a mature tool. It's got a lot of features. It's not just the feature that I would show here. Basically what it does, it extends the Python language, particularly by C imports, so kind of C level importing libraries. Then what it does, it translates the the Cython source code, which you would use with the extension .pyx, which comes from Pyrex, which is the language that came basically before Cython. And it translates it to C and C++ and compiles it into a Python module. So it includes what it adds is static typing. We'll make use of that. You can also conveniently code and bind C or C++, and so on. So it's very powerful. So if we just Cythonize the function that we implemented, and I'm taking a shortcut here using another IPython magic with a $% Cython -a. So I run it on the implementation, and I'll actually switch to the notebook view, just to show you the output here. So the output, if you put -a, would mark by the yellow color the pieces of the code that are not optimized, that Cython thinks have too much interaction with Python. So already from this color, you might guess that we are not optimizing the code. To make it better, we can static type some of the variables that are used in the function. That's what I do here with these cdefs, and in particular this one. And also on the interface, you see I already put numpy array. So this function now works only for numpy two-dimensional arrays, and it uses the static typing to see the effect on the color. So I think if you compare, if you remember a bit, that picture before was much more yellow. Now you're getting less yellow, which is good. So Cython doesn't like yellow. By the way, if you analyze this, there's this plus sign and button, and you can actually see what amount of work your Python interpreter is doing internally to get you the very nice language and the high abstractions that we all love and that we use to code very fast. Okay, so let's test these two functions. Okay, I've done that before, so believe me, it really ran well. And see the performance. So actually, the first version, or the 0 version, is a little bit slower. Okay, it's on par with the Python version, which is what you should expect in this case. It's not in general that if you run a Cython on your Python code, you would not gain a performance. It's just because we have just a tiny function where we just don't get anything. Now the second version, so version 1, is already quite faster. It's in between the loops and NumPy version, so we are probably in the right direction. And if you then look into the usual tricks that Cython offers for these calculation, these optimization, you would find that if you switch off checking the array bounds and disabling negative indexing, so you switch off some of the fancy, nice features that we have from Python and NumPy, what you get is less yellow, which is good. Here it comes. And if you look where the yellow lines are now, you probably don't see it really, but these are just the yellow lines that we can't get rid of because we just need to interact with Python somehow, and we need to deliver Python objects back and import Numpy and so on. And what we actually gain is a performance that is much faster than Numpy. And I think that's a huge gain. So we've beaten Numpy by an order of magnitude by starting with a dump style for loops, and then by just adding a couple lines of Cython, decorator, and static typing. Yeah, so we are really happy with that. Okay, maybe someone will tell you, okay, you should do it in Fortran. That's like the language for doing numerics, and it will just beat your Python totally. So let's try. We are lucky that Numpy guys were so smart that they created this F2Py code that people use a lot to wrap Fortran or C. So then let's not be shy and do some Fortran. And I actually like the Fortran, at least the modern Fortran. It's not a bad language. So the implementation for this case looks pretty much like the Python loops. I mean, you can spot the nice double precision wording. So that's the Fortran way of doing stuff. Okay, so there's not that much work that we need to do to actually get a Python module out of that code. So we run F2Py. We use actually some switches that we don't need. So we just put F2Py. We read the documentation. And we know that we just put the source code file name and -m, the name of the module, and it should run. And if you then import the module and look at the documentation of the function that you just compiled, you would see the interface. So F2Py actually understood the dimensionality, the types, and it would report you that in the documentation. So it seems the interface is what we actually need, and we can test if it runs well. One thing to remember is that Fortran uses a different ordering than C. So to get the best performance, you should have the Fortran ordering in your matrices or arrays. Now it runs. The time here is under 7 milliseconds. I'll show you the comparison in the plots. But when I see this, it's quite different than what I get on my laptop. And here we are touching quite some low-level properties of your hardware. So and then the compiling switches and so on. So you might even want to tune the compilation further. So this was Fortran, and the last tool I'll show you here briefly is Numba. And I really like it. It's a super simple tool to use and pretty powerful. It does not do everything. It's not almighty, but it does it. Basically, it uses LLVM on the bottom. It's built for data and science, so for us, and it's straightforward to use. And it compiles your Python code into a machine code. So for our use case, we can just take numba.jit, which is a just-in-time compiler decorator. There's a couple of options. I'll use the default for now. One particular interesting one is no Python, which sounds scary. But it really compiles Python, but internally it would refuse to run any code that depends on the Python runtime. It would fail for our case, by the way. But there's a workaround. It's not too difficult to make it work. But there's no gain on the performance. So what I do here, I just decorate my loops function. So again, not the NumPy one, and then compile it, or just in time compile it with Numba. It's the same as in Cython. It works. Of course, I would not show you if it did not. So the time is now comparable, if I remember well, to Cython, to the best Cython. So here it goes. So we have Cython 2, Numba, just very fast compared to the others. Fortran following, but when I ran it today on the laptop, Fortran was, I think the second Numba was the first one, and Cython the third one. So don't draw too many conclusions from the ordering of these three. Okay, so I think we've done pretty good business on optimizing that small function. Now, I also said we should look at the memory usage. Here I'm using a tool from our speaker from the last PyData meetup. And I will just watch the memory using this tool. And okay, here in the bottom, I run it for my original X array, which is not too large, right? It's 1,000 times 3. It doesn't take any memory, especially the peak memory is 0. That's good. Now, when I try to run that on a little bit larger problem, so 5 times n, 2 times n, so I call it XL here and run it on XL. If you can see it from over there, there's a peaked memory of 1 gigabyte, which can be a little bit unexpected. It's from the broadcasting thing. So if you think about what broadcasting does, it adds one more dimension, and so it creates a potentially huge array. And if you just add instead of 10 and 4, instead of 5 and 2, you would add a little bit more elements. You would run out of your memory if you are not running on a big computer. So be careful with that. And actually, if you look at what the Numba version does, is that it solves this issue for you, and it's kind of comes out from the solution. We are not constructing the big array. We are just looping. So that's another problem solved by Numba. Cython would be the same here, of course, because it's doing the looping similarly. Sorry. So yeah, the first quote is from this presentation, so feel free to cite it from now on. Okay, so I think parallelization is kind of comes along with optimization. It can be a way to make your code run faster. My advice is try to use what's available as much as possible. Try to be rather on the high level. Don't do the low level parallelization, although I'll show you the low level today more. Typically, you need to run something like a map on a number of inputs. So you can use, you don't need to parallelize the internal of the code. And also avoid threads. I'll show you threads again, or that we can use threads, but the advice is don't try to do it yourself. if you're not well aware of what you are doing, and also because the infamous GIL, which would prevent you from doing threading, but it's actually helping you not doing terrible mistakes. Right, so in Python, in the standard lib, there's a module called concurrent features. If you read the documentation, there's not too many, not too much stuff in there. You find two basic classes, executor, which is something that would execute, as the name would say, the functions in either a thread pool or process pool, or any pool that other libraries can expose. And there's Dask or PyParallel, which are quite well known. Maybe less known is that there's also MPI for Py, which is a message passing library for Python, which also exposes an executor. That's fairly interesting. And then you have the future class, which is an asynchronous result, a promise of result, which is returned by the executor. So just a simple example. I won't use it for our problem now, and I'll actually probably make it very fast because I'm running not out of time, but close to the end. So the parallel map, if you have a number of inputs you want to map a function on, just use an executor that is suitable for you. Now, thread pool might be usable. I'm using it here now because it's the simplest one to spin off, but it might not deliver you any parallelization. It can, though, especially with Numpy, Pandas, they often release your evil GIL, so you can make use of threads if you are using those libraries. So what you get are those future results, and typically you somehow need to synchronize. You need to wait for them. So there's wait function in concurrent futures, and then once these are done, you can just collect the results in a list, for example, as I'm doing here. There's also a map method of the executor, which would do about the same, but would just yield a generator. So you would work with that a little bit differently. You would not get the futures themselves here. Now I already mentioned Dask and PyParallel that offer very easy to use scalable cluster executors, which can either run on your local machine or can even run on a cluster. And so you just run on your colleagues' laptops. You just run one single command and you can get a cluster out of your office in a minute or so. This is, I think, what I just said, so let me skip that. And now a little bit on parallelizing the code that we actually targeted today. I'll use Numba again. There's a parallel argument to JIT, which does what it says it does, is try to parallelize the code. You should also use p-range, so a parallel range instead of range. You should see if the code is easily parallelizable, which is our case, an increase of performance, so usage of more cores at the same time. I mentioned MPI for Py. Aside of executor, you can, of course, use it for rather large-scale scenarios where you need to send messages, typically short messages, in and out from a pool of processes, potentially across your large cluster, and it makes it easy to send Python objects. It's also performant for NumPy arrays, and you don't have to use the raw MPI protocol, which is rather simplistic, and there's just primitive types that you can you can use. And I'll also touch just briefly what Dask offers in its high-level collections, and can also do some parallelization. So for Numba, it takes just the same JIT with parallel equals to and replacement of the first range by p range. If you go through the loop, you would see that you can really make the inside of the first loop or even the second one independent. It doesn't matter how it's ordered. And if you do that, you assert that you are happy, you execute the parallel version or time the parallel version, you can get times that are really faster than your previous Numba run. So it makes use of your threads or cores efficiently with almost zero effort. That's another good result, I think. And now just really fast scroll through Dask. I'll show you how array, which is one of the high-level collection, can be used, what it is. But please consult the documentation or the Dask tutorial to learn more. So here I create an array collection. So that would be a Dask version of a NumPy array, but it's made for out-of-core distributed calculations. Since we will use it for a small problem, it's not really helping us, but we can see the principles. One of the principles you need to follow is that you specify how large chunks of the data you have. So, and once you create that object, you have the delayed function or decorator that you use, and that Dask uses to actually create a call graph instead of executing functions and then executing the call graph. So this is how you can create a delayed function from an existing function. But if we do actually want to implement our pairwise function, we can just plug in the Dask array into the place where we have our NumPy array, and it would create the call graph, and we can do it step by step, in fact. So I'm taking the first step here. So you see it would chunk into two and then schedule the calculation, plan the calculation. Okay, so there's two more steps with the sum and square root. Here's the final graph. You check that it's doing the right thing. And actually the time it takes here on a local computer is slower, but not too much slower than the Cython version. So it, in principle, should scale better for large arrays, especially if they don't fit into your memory. It would be able to do it. So this is the way if you need to scale for larger problems. And I'm not going to show this because I would like to end with this slide already. So my summary is you use Python for numerics. There's powerful tools that exist for optimizing calculations. You can have very efficient optimization with a little effort with the JIT decorator from Numba. Be careful with NumPy memory consumption if it's doing broadcasting. By the way, there was a quote from Wes McKinney, the author of Pandas, and his rule of thumb is that your memory should be something like 5 to 10 times larger than the size of your Pandas data frame, which is what people might not guess if they come to Pandas. And then one of the reasons is of course this, because Numpy is used heavily in Pandas. Also remember concurrent futures. If you have not found that yet in your Python library, look it up, use it. And for referring to these slides, it's all available on GitHub for free. Thank you for your attention.
Thanks for a nice talk. And so there are some questions on Slido. That's very good. I'm really glad that you have done that. But first, we should probably ask if there's someone who is not shy to ask aloud his question or a question. Probably not.
Maybe
okay. So sorry. Let's see.
I'm not sure if I can hear on the video, so maybe you should then repeat the question. Regarding Dask, we have seen the visualization of the computation graph, was called like that, and it reminds me a bit of TensorFlow.
There's some similarities for sure. There's a lot of tools that would actually construct a call graph and then execute it on engine and workers. If you look into Spark, it would be similar also. So TensorFlow, I think, is different in that sense that you have more emphasis on tensor algebra in the nodes of the graph, while here it's well, Dask would have also the algebra, but you can also put arbitrary Python functions.
Okay, so another physical question?
Maybe you try to compare your routine to some other languages like, I don't know, C or Java.
Or Fortran. Yeah, so the question is to compare the performance or well, I think the answer is it depends again, because as I showed here, you can be on par with the Fortran code, which I think is spectacular almost. Fortran would be on the similar speed as C. The coding would take you much more time if you start from C, for sure. So this is one of my first advices is because in Python, if you are a decent Python programmer, you would code fast, prototype fast. You find your bottlenecks first, and then you can fall back to either some of these tools and even maybe Fortran, C, C++. Java is a bit difficult to interface to Python. So with Java, you are a bit drifting out of this meetup community.
Okay, so then let's give some chance also to Slido, so to encourage you to post more questions. So the question that actually got 2 votes, a reminder for the second part of the meetup, it is possible to vote for questions that you want to really be asked. Question.
I could not vote.
You could not?
You say, no, go ahead.
Okay, sorry. The question is, the result, should we use Numba for everything? Is it the optimal tool to do everything, or is there any place for Cython or F2Py?
No, we can't use it. We certainly can't use it for everything. And I think the way to use it is to localize what needs to be made fast, and then compile that piece. One of the reasons is that seeing errors from a Numba optimized function is more difficult than from Python. So if you don't need that performance, don't decorate it, don't use Cython. And Numba, at least at this stage, is not replacing Cython completely. There's a lot of features that Cython has and Numba does not.
Okay, thank you. And the last question, if you can give a brief answer. Have you tried PyPy?
Yeah, there was actually a discussion on one of the function that I'm profiling basically, and I'm not using PyPy. I admit that maybe I should try it more often, but the reason I'm not using PyPy is the lack of all the Numpy ecosystem. So PyPy is awesome. It's got a lot of just-in-time compilation features. If you implement that code, and actually thanks to people that are sitting somewhere around here that did the benchmark just in time before we started this meetup, it runs very fast if you implement it in Python using lists and running on PyPy, which is very good. Even Python can run faster than indexing NumPy arrays, but NumPy would then it would not scale up or out if you like all the NumPy bound tools and the algebra that already is in NumPy and the tools around. So I think that's still a shortcoming of PyPy. Not sure if it can be resolved, but I'm not that much of an expert on PyPy, really.
So thanks again, and this ends our first half of this meetup. So thank you again.